So my name is George Wilson. I'm also working at Delphix. Before that, I worked at Oracle and Sun. So I've been involved in ZFS for quite some time. The stuff I wanted to talk about was a little bit of some of the recent changes that have gone in with regards to pool performance. I'm going to talk a little bit about like full pools and imbalanced pools. How many people run kind of imbalanced pool configurations? So our customer base is very well known for having imbalanced pools, and this is the case where you start off with your pool configuration, you have like 4 LUNs, and you start loading a bunch of data, and then sure enough, it's like, I'm out of space, I need to add more space. So now I have 4 LUNs that are full, and I add 4 more LUNs. So I have like this big disparity in ones that are full and ones that are completely empty, and performance can nosedive from them. So that's a problem that our customers face a lot, just because they're always adding and adding more data. If somebody has like a storage appliance, they may start off with this massive, lots of terabytes or petabyte of storage, and maybe they don't see that issue because they've added all at once. Our customers don't do that. They tend to add it kind of piecemeal. So ZFS kind of like historically has had ways to deal with this, but they never really were very aggressive. The way that it would work would be that you simply, it would figure out there was this disparity in space between multiple LUNs, and then it would try to add or allocate a little bit more to one LUN than the other. In many cases, that little bit was like 25% more. So, it's not a lot when you have a huge disparity, and we needed something that was a little bit more aggressive, especially for our customers.
So that works well when you have to just keep them balanced.
Yeah.
If they're already balanced and you're freeing some and you're allocating some more, it keeps them balanced.
Right. So like if you're, 39% full and the other one's at like 38.75% full, then it's nice because it kind of brings them back in balance, and they're both 39%. But when one's at 90 and the other one's at 0, you can't get there and balance them out fast enough. So we came up with this thing, which is in OpenZFS. I don't think we really talked very much about it, but it's called ZFS MG no alloc threshold. And the whole idea behind this is it sets this threshold of free space that you want to maintain on your device. So as long as there's that much free space on the device, that device is eligible for allocations. If free space on that specific device drops below that threshold, then it's no longer considered eligible. So just to compare the two approaches. The original approach was you start off with a couple spindles, you start writing some data, you're filling it up, you get to this point, and now you're like, I need to add more space. So I add some more spindles, and now I'm writing data across all of them because ZFS will automatically give you striping. But all we're doing is we're filling the ones that are mostly full almost all the way up, and we've just barely made a dent on the ones that are empty. So that's the way that the old algorithm used to work. What we did was we made this change by having the MG no alloc threshold, such that, again, I can fill it up, and once I get to a certain point and I add my additional disks, this time when I actually start to write, I start writing much, much less. In this case, these writes that we allow to go to the other devices are the minimum sized write that you can accept in the pool. So 512 bytes is what you get on those devices, and that's simply just because if we fail 512 byte allocation, then we can't gang that, so that turns into an error. So we at least allow that size to go through, but then we write big data onto the other devices. And we write until they all come up to the same threshold. And then once that happens, then you're allowed to write the same amount of data to all devices. You start striping across them all once again. So that was a change we made because we needed to force things to get to these new devices much, much faster. Yes?
The old algorithm was already biased to new readers and new devices, right? The way they were just not aggressive enough.
It just was not aggressive enough. So you would see instances where, without like RAID 0 mirroring, so just simple stripes, we have a stripe width that effectively says you do like 512 meg, I think, per device before you round robin to the next. And it was like you do 400 to one and 600 to the other. So it was like it wasn't balancing it enough.
If you didn't add more space, it would continue to write to already at the threshold.
Yes. Yeah, so the idea behind it is that once you hit that threshold, that device isn't eligible, but if all devices are beyond that threshold, they're always eligible.
Is there footage initially too where you're just doing small writes if you have large IOs?
So in this case, the small writes are metadata writes that happen to be 512 bytes that I can't fail. So if you spend any time in like the Metaslab alloc code, if you try to write the smallest unit that ZFS allows, so 512 bytes, if that ever fails, then that's considered an IO error, and then that causes the entire pipeline to stall. So if you ever try to write to that device with 512 bytes, then it better succeed, because we can't gang it. So ganging is where you try to make up the same size block by kind of chaining it, splitting it apart and creating two smaller buckets, but we don't have anything smaller than 512 bytes. So
I mean, it sounds like this is an ease of implementation issue rather than we intentionally made it because that's the right thing to do is to allocate 512 there. It's just
correct. It's like
it's kind of an artifact of we wanted to implement it in an easy, straightforward way.
So this actually prevents us from having the I/O mechanism stall, and we allow very little data to go to it. If you ever watch this like in a real pool, you'd see like tens of megabytes going here and like K worth of writes going to the other.
George, is it accurate to describe this threshold as a bit of a kludge?
It is a bit of a kludge, yes. Again, this was, so as Adam kind of alluded to earlier, somebody was asking the questions like, how do we do these performance changes and how do we roll them out? We've been observing the performance problems and then we've slowly been implementing them, but this isn't enabled by default on OpenZFS. We've enabled it on some of our customers so that we can see how it behaves and how it performs. And what we're learning from all this is that as we run across these different scenarios and we discover something that's effective, we can find ways to actually leverage it and enhance it. And I'll get to that. Yes.
Did you remove this recently?
No.
Oh, okay.
That's another thing.
That's another thing. Okay.
That was the imbalanced 1.0 or 1.5.0. Yeah.
Does this affect your read performance on your workload that you guys care about?
So for us, what you end up with, like when you're in this situation, the read performance typically means that most of your data is actually here because it hasn't been striped across. So for reading, it's not that big of a deal. Where you're losing is write bandwidth, because in the case of the new enhancement, you're writing most of your data to these devices. So instead of getting 4 spindles of bandwidth, you're actually technically getting 2. But for our customer base, and I would assume anybody who's kind of been in this behavior where they start off with some disks and are adding more, they were already getting 2 spindles worth of bandwidth. Now they're getting 2 spindles worth of bandwidth.
Well, but the problem is before they weren't actually getting 2 spindles worth of bandwidth because it was all random writes.
Yeah, it gets. The problem is as these things fill up, you get to the point where you're spending so much time here. First of all, finding a block to allocate. Second of all, every single write turns into a random write. So latencies just go through the roof.
I'm just curious because a lot of times you'll write and then read it back quickly. You're only using 2 spindles, so then that read comes off at 2 spindles instead of 4.
Correct.
Yeah,
I mean, if it wasn't wasn't cache or whatever, you had to go back out of the disk, you'd be coming off with 2 spindles in those instances. So the other thing that we've been working on is trying to understand free space. Again, Adam asked the questions like 30,000 segments, was that a large number? We'd never looked at the number of segments that actually made up a space map. everybody was happy, right? Everybody's running ZFS. Nobody really complained about that. It was like, yeah, it's all good. Well, so you look at the number of segments, and that doesn't really tell you very much because you don't know how the free space is there. You could say, you can look at one MetaSlab, and it may have 30,000 segments. It may have 250,000 segments, and it has 4 gig of free space. It's like, what does that mean? I have no idea. I have a lot of segments on one, I have fewer segments on the other, but it's still high, and I have the same amount of free space. So the thing that we wanted to do was to create this histogram and start storing this on the pools. So there's a new feature flag that's out there that you enable, and it upgrades your space map objects to start storing histograms. These are just power of 2 buckets of how the free space is comprised on disk. So it gives us the first time we actually get a view of like, how is that free space made up? Now we can figure out that 4 gig might be nothing but a bunch of 2K segments. And that might explain why we have 250,000 segments. They're all really, really small. Performance is going to be really, really bad on that. Any IOs that are trying to go to that. The other thing, so today what's available is you can get histograms for MetaSlabs, which is misspelled. We've now enhanced this to actually have it for devices, so you get histograms on a device level, and you're also going to be able to pull this on a pool level. So we've been spending a lot of time kind of adding more observation into the way that free space is there, so we can have a better understanding how to deal with fragmentation, and especially how do you allocate in a highly fragmented pool. The other thing that we added was a new block allocator, and again, this is not enabled by default, so this is something that you could play with. The whole idea behind the allocator is that it actually keeps track of the largest segment on a MetaSlab, and then just simply consumes everything within that segment, and then goes to find another. The current allocator that's been shipping for a while actually has 2 modes. It has a mode where it tries to find everything based off offset. So it's trying to keep things in offset order. So if you last allocated at offset 1000, it's looking for allocations that are close to 1000, but slightly greater, and that will satisfy that allocation. Once you get to the point where the space in that MetaSlab is mostly consumed, then it starts going into a best fit mode where it's like everything's going to be random right. So it has kind of this 2-mode property. This does not. This would actually always goes to the large segment and then consumes that segment in its entirety before moving on. This may help some workloads out there. We've done some performance testing with this, but we did not enable this because we're kind of limiting how we're rolling out performance changes. We're also changing the way that we actually handle the MetaSlab selection. So how many people are familiar with the way that we allocate on disk, the way that the ZFS does allocations? So I'll just kind of briefly go into it. ZFS kind of does this like there's 3 different phases to allocations for when you're trying to allocate a block. The first thing that it does is it determines which device to allocate from. So it's first going to pick a device, and then within that device, it's going to actually look
MetaSlab group, right?
Yes, or a MetaSlab group. For those of you that are familiar with MetaSlab groups, you can think of those as devices. Then it's actually going to look within that device at any one of these 200 MetaSlabs and pick the best MetaSlab to allocate from. It's going to then, within that MetaSlab, go and find the best region on that MetaSlab to actually satisfy that allocation. So it's device, MetaSlab, block. Effectively, those are the three layers that it goes through. The problem that we had is that the MetaSlabs, the way they're ordered, only took into account free space. And again, we've just talked about how we didn't know what free space, how free space was comprised on that MetaSlab because all we knew was a number. Well, now we actually have some histogram information. We have the way that the MetaSlabs are, how the free space is broken up. It gives us the advantage to actually come up with a new weighting mechanism. So we've come up with a metric to measure fragmentation at a MetaSlab level. And we can now use that as a weighting mechanism to weight metaslabs that are highly fragmented down, weight metaslabs that are less fragmented up. So this gives us the ability to actually pick the best metaslab, truly the best metaslab, to go do allocations. There are some things that we've been discussing for things like, does it really make sense to always go after the best metaslab? And we've had this conversation about, like, what if the workload is low? There's not a lot of writes coming through. Well, if the demand isn't there, then maybe we shouldn't pick the best one, because all we're going to do is Swiss cheese it up. Let's wait and do the best one for when there's actually a lot of workload to be done. So that isn't implemented yet. We've been kind of kicking that around, but that's an idea that we've had of trying to now take, this is again, kind of learning all the things that we've discovered so far of, we know now how much workload is coming in based on the right throttle work that's been done. So we can keep track of how much dirty data there is to be written. If the amount of dirty data to be written is actually very low, then maybe we don't try as hard to go find a really pristine and awesome metaslab. Maybe we just say, okay, you're going to get, this one that's mostly fragmented, because we can waste a few cycles there simply because there's nobody that's really requesting a lot of work from us. So we think that could be a win for us. It could also mean that these pools that have lots and lots of segments, now all of a sudden you start filling in those holes, the number of segments goes way down. Now it's not as big of a pain point when you actually have to go and look at those metaslabs.
Just another point on that, we can actually use that idleness in the system, just to draw a finer point on it, to optimize our space maps. So knowing that rather than having 30,000 segments, if we can go find exactly the right place to drop that puzzle piece, then we only have 29,999 segments. And if we do that enough, we can actually make it a little more manageable. And do that at a time when the performance demands of the system are not high.
So slowly we're trying to take the information that we're learning to be much more intelligent about how we actually pick the right block, pick the right metaslab, and you'll see even pick the right device. The other thing that we've done is we've actually added this preloading of metaslabs. So what we've learned is that anytime you actually have to go load a metaslab while you're in the allocation code path, so you're in the right context, is very, very painful. So we now can figure out which ones are the best metaslabs on each device that we anticipate we would need to load, and let's go load n of those every single time we finish a transaction group. So they're already loaded in memory, they're in hand. The next transaction group comes through, he goes to do allocations, everything's already there. We don't actually have to go spend I/O cycles to go read them and load them in. Hopefully that's enough. Again, that's another area for, I think, more future work where we can determine what n is based on kind of the information that we're getting about dirty data that's coming in. So if we know that we're getting, gigs worth of dirty data coming in, then n better be large enough to handle the gig that's going to, get synced out in the next transaction. So today that n is hard-coded, but we think there's more future work that can be done there where that actually becomes dynamic. Questions on this stuff? Yes?
So also, would it make sense if we knew what kind of writes are coming in? What size writes, so that we know which ones to look for?
Yeah, so if we knew, so it's going to vary based on what record size everybody has. But yeah, once you kind of have an idea of like what blocks are coming in, you can kind of assume that, say even with compression, I'm going to be looking for like an 8K block if that's what your actually record size is, an 8K block. Maybe I can fill a 4K segment, but at least I can get an idea that I have these number of 8K segments.
What are the largest that we saw? And one of the problems that we saw was 128K showing up, and we had this famous one where we'd just we'd search through all over, and then we'd never
you'd never find 128K segments. Exactly. Yeah.
Are you talking about histograms?
No, this is more of trying to understand, like, if we know the types of IOs that are coming in, I think this is more the piecing, finding that right puzzle piece. It's like, how do we know which puzzle piece to go after? If I know that I have, 108K segments that are coming in, and that's my low period, then I'm looking for metaslabs that potentially have 100 open spaces of at least 8K,
But not too much more
But
than
not
that,
much
because you
more
want
than
to fit it
that.
exactly.
Because I don't want to go after one that's got a bunch of 128K segments. I'm looking for the one that I can just fit the puzzle piece in. So it's kind of building on the same idea that we've been discussing. So I mentioned that we've now added a fragmentation metric to each MetaSlab. We're exposing that also on a per device and per pool level. So we'll now be able to see the fragmentation metric for each device and each pool. So this is all based on that same space map histogram data that we're now keeping on disk.
So it gets updated every TXG.
It gets updated every TXG. If you've spent any time in the MetaSlab code, it's not going to be 100% accurate every single time, because there are cases where we actually do freeze, where the space map isn't loaded, so we don't know all of the segments, but we do try to change every single time we reload a MetaSlab and we do operations on it in syncing context. We'll go and actually refresh it to give it an accurate view, but it can kind of fall off a little bit over time and then get refreshed. So what's interesting here is, just as we were using this fragmentation metric to weight a MetaSlab and try to find the right one, now we can do a similar thing. If you go back, when I was talking about the imbalanced LUN, we had this hard-coded value. Well, now what if this value kind of becomes the metric of which devices do I go after to actually look for allocations? Ones that are more fragmented, I try to avoid. Ones that are less fragmented, I go after and start to do allocations for it. We can change the way that we actually do device allocations going forward. We can select ones that actually have more free space and are more eligible for allocations based on the fragmentation metric. Yeah.
What does 50% fragmented mean?
So fragmentation is kind of,
It's nebulous.
yes, it's very nebulous in the ZFS
So
world.
here the truth. Here are things we can assert. 100% fragmented means that it's all in the smallest chunk size possible. So like all 512 byte free chunks.
Or 1K, actually 1K
Oh,
or
1K.
less. Yeah.
In
So I don't want
100%, 0% fragmented means it's all more than
16 meg.
16 meg.
So and again, this is it's a little nebulous, as Matt was saying. We're trying to come up with a way that we can create a relatively good metric that makes sense to us here. And the idea was that a 16 meg segment is probably large enough to be able to satisfy most allocations of any workload that you generate. We may find that 16 meg maybe isn't, but at least from some of the data that we've seen, 16 meg seems to be satisfactory and does not cause performance problems. So if we can say that anything that's 16 meg, any segment that's 16 meg or larger is considered not to be fragmented, we use that as our first metric. And then we step it down as you go from 16 meg all the way down to 512 bytes. So 1K is, I think at 1K, if your segments are nothing but 1K, is 100% fragmented. So when you see,
there's like a table that
Yeah.
tells you like this chunk size. If it was all this chunk size, then it would be X% fragmented, and then we just weight we weight everything based on the histogram of how many there are in each chunk.
so then we factor all that in. So this gives you an idea that you have things that are probably somewhere in the 4 to 8 meg range of segments. Actually, probably less than that. I think 50% might be 128K segments. So most of your segments are 128K. Although there's probably, if you were to look at the real histogram and
Look at the histogram of CDB or something.
yeah. So we've added to ZDB the ability to actually dump out the MetaSlab information, the space map information. And actually there's a ZDB minus M, so maybe what we need to do is just remove it so it never prints under D to solve your problem. I don't know why.
Is frag effectively like an average, a sort of average of the histogram?
Yes, yeah, it's effectively kind of like an average of the histogram segments. Space on the segments.
Yeah, I mean, you can't, boiling it down to one number is it's never going to be able to give you the whole picture, right?
Yeah.
This could be all blocks that are 128K, or it could be one that's 16, 10 that are 16 meg, and then 1,000 that are 1K,
Yeah.
right?
We talked about
You gotta
several
look at the
solutions
history.
and this was the one that seemed to fit and nicest of being able to take into account the entire range of all free space segments in the MetaSlab and still represent it as one number. But the ability is that one number then gives us the opportunity to make better decisions of when we go to actually select devices.
Histograms themselves, and you store them on disk, or they in the objects.
So the histograms are actually stored as part of the space map object. So they're in the bonus buffer of that object. So one thing to note too is if you're upgrading to this feature, the space map objects have to actually get reallocated in order for you in order for them to use the larger bonus buffer. So older objects won't have it, newer objects will. You'll see if you upgrade, fragmentation won't actually show up in zpool list until, like, I think I have it right now at 50% of the MetaSlabs within a device have been upgraded. So if fewer than 50% have been upgraded, then you just get a dash there. It doesn't show anything until over time they upgrade. We're also adding logic to actually kind of speed that process along, just because we definitely want to get more information about free space so we can understand how to improve things even better.
Say you made the bonus buffer.
The bonus buffer is, yeah, on the space map object. Yeah, just on the space map.
We're running a little short on time.
Okay. Question?
If we're short on time, I can defer it.
Okay. And again, as I was mentioning, this is probably where we go next, is taking this fragmentation number to go and look at deciding which device we're going to look at and go do allocations for it. We're also introducing this allocation queue. So in the pipeline itself, what happens today is when you go do allocations, we hit a point where we actually fan out to a bunch of threads and go through the allocation in this kind of, parallel fashion. The problem with it is that if you're, allocating data, and maybe metadata, when it all gets fanned out, it kind of all meshes together. So you get into a mode where you could get allocations on the same device of, larger block, smaller block, larger block, smaller block, and over time this can add to the Swiss cheesing. So by having this allocation queue, we can actually order these based on the way they're issued. So if the ZIO tree has already built it up to have a bunch of data blocks, which it has, a bunch of data blocks that should be allocated first, then they would actually get allocated first. The other idea behind this, and again, we'll probably not enable this when we actually push this upstream, just because we want to see how it's going to behave. The idea behind it is that as devices start to allocate and write more slowly, then chances are they're probably more fragmented. So if every device now has an allocation threshold, effectively the number of allocations that they have pending, if a device has already reached that, when we go to allocate from the next block and issue it down to the VDEVs, we would find that certain devices already have reached that threshold, so we just skip over them and find one has already processed them. More than likely that device either doesn't have as much workload or has run through his queue much faster, meaning that he's probably doesn't have as much fragmentation. I think that's all I have. Questions? Catch me afterwards if you want to discuss this. I'm interested to hear how people are experiencing, what problems people are experiencing with like full pools. And
George, when do we, is 200 MetaSlabs the right number?
It was a question mark on your slide, it would be a question mark on my slide. I think it's not. I don't think that the thing that we've discussed, and the thing that makes more sense to me is MetaSlabs that are actually size-based. The problem you have there is that, and I think the original intent of them being 200 was to allow you to have devices as small as 64 meg, so that you could carve that up 200 ways, and if we made our MetaSlab sizes be 2 gig, then obviously you wouldn't be able to have that. But I think that a fixed number doesn't make sense, in my opinion. I think we're better off actually trying to, rather than say we're going to pick a number, let's pick a size, which may limit that and say our smallest device that we'll ever support is, a 4 gig device or an 8 gig device or whatever that size is. But I think that's where there's an area for investigation.
Yeah, please keep 4 gigabytes.
4 gig is the
Please, yeah.
There's actually a lot of benefits to something like this for the ZIL, because the ZIL, even though it uses MetaSlabs to do its allocation, it makes no sense there, because all you really want to do is you want to scan and do effectively plus or cursor-based allocation on a ZIL device.
Yeah.
That's really what you would like to see. Is you'd like to say, I start here and I keep allocating until the end, and then I wrap around and I start over. And on a solid, state device, you're obviously doing better wear leveling than that. So,
Or no wear leveling.
Or effectively, yeah. So I think there are benefits to actually getting rid of the MetaSlab sizing, because today we would chunk up that 4 gig device, try to chunk it up 200 ways. You end up with small MetaSlabs that you end up having to toss back and forth, and it doesn't make as much sense.
Right.
But Adam, to your point, I think that's an area we need to go and really.
Have you guys done any investigation or tweaking that?
We have not. We have not looked in that area to see what it should look like. I think that there's going to be, when we actually go down that route, because I think the answer is we will go down that route of looking at a better solution. There's the upgrade implications kind of have to be considered there. Customers that already have 200 MetaSlabs would probably fall in nicely, and we have to make sure like things like spares and mirrors and all that stuff all just works.
I'll just throw out that it seems to me that maybe the allocator is avoiding the last 30% of the MetaSlabs a little too.
Today?
Yeah, if you look at the ZDB output, it doesn't use those last 30% of the MetaSlabs until the pool's like 70% full.
And part of it is that the weighting factor that is in there tries to provide a bonus to MetaSlabs that are like lower LBA range.
Right.
So in a way, it's like you have to really, really work hard to fill up the first, half of your device before it even starts to consider something at the very end. Yeah, agreed. And I think that with the new MetaSlab fragmentation weighting, that actually is going to come into play much earlier, because you're going to find that even though I'm still allowing you to have a higher weighting for lower LBA ranges, as those get consumed, their fragmentation metric goes way up, and you start losing that doubling effect. It starts to go away, which makes the ones at the end more enticing to go do allocations.
I guess that brings up another question. I mean, that only makes sense for spinning disk, right? That the lower LBAs will be faster. Is there any thought of extending it to be aware of like non-rotational medium?
I think that there definitely should be. I think that we should look at, once we know that we're not dealing with a spinning device, then it's very easy in the MetaSlab weight code to say this device has, should not even take that weighting into account.
Well, and not just solid state, but the kinds of devices we plug into, which are spinning disk, but the LBAs, like the mapping,
don't
doesn't
make any sense.
Yeah.
So why we're biasing it to, to one part of it doesn't mean anything in terms of how it impacts real disks.
Agreed.
Yeah, definitely the more we know about the device, the better decisions we can make as well.
Cool. Thanks, George.